All right, so these are from 12.3. If you weren't here yesterday, we did word problems on 12.2 for which there's a screencast. My computer's now stuck. Okay. For which there's a screencast, but it's okay if you haven't watched it. These are independent from what we did yesterday. Okay? All right, so these are the word problems that pertain to 12.3. All right, so here's one that says, Tim drops a rock from 1,200 feet. Okay? The position of the rock, t seconds after, is given by this. So this is position, right? All right, so the first thing I do when I see a problem like this is, first of all, position and that, right? I do some sort of marking so that afterwards when I go back, I know what pertains to what. And then units. Units are important. Units are important because position is given in what? Feet, and then time is in seconds, right? So time is in seconds. Right, so I do tend to underline those so that afterwards, like I'm frazzled, I'm taking a test, I don't know what's happening, I could just go back and pick up the units, okay? All right. I'm not going to even start solving this problem yet. I'm just going to visualize it first, right? So Tim drops a rock. What's happening to this rock? It's falling, right? Okay, so look at the position function. What kind of function is it? It's a what? Negative what? It's a parabola. It's okay, what do you mean by negative though? It's facing down, right? So it's a parabola, which means if it's a parabola at the center of it, it's got a what? A vertex. Is it a minimum or a maximum here? It's a maximum. Okay, so now we haven't even solved the problem, right? But it's important for us to know that the position here is going to have the characteristics of a quadratic function, right? Okay, now let's still think about this because we know that we're doing limits and this and that, right? And limits, usually we're looking at limits at infinity and as t approaches 0. So at the very beginning of this, when t is 0, forget about the equation. Where is this rock? At 1,200 feet. Does the equation tell you that? Yeah. Right? It does tell you that, okay? And then, so you visualize that this parabola is doing what? Is it opening up or down? Down, so that from the maximum, it's going in what direction? Down, okay? Does that make sense to you, that the position will eventually be lower than it was in the beginning? Okay, great. So now I have such an amazing view of what this problem is going to look like, right? Okay, so now let's start reading this. Okay, how fast is the ball falling after 4 seconds? What is that asking us to find? S of 4, is it? V of 4, right? S of 4 would have been what? Position. The position. Okay, so that's V of 4, and how do we find that? Oh my God, what did she say? Say it again. That's the slope at a point, right? Instantaneous velocity or instantaneous what of what? Rate of change, right? Remember what I told you guys? Instantaneous rate of change, slope at a point, or remember? I still haven't tapped anyone and asked that question. Then we have, when will the rock hit the ground? And then I'm being asked, find an expression for the instantaneous velocity vt of the rock. And I purposely put those questions in that order because you see that, and then you start finding v of 4, and sometimes we want to plug in the 4 in the beginning. Here it's asking me for v of t as an expression. So I say to myself, you know what? Maybe in the beginning here, I'll find v of t as an expression, then plug in my point so that by the time I get to c, I have already solved it. Does that make sense to you? Okay, so let's do that first. So let's find v of t. Here's what we're going to do. I'm going to race you to it. Okay? Okay, let's go. Let's have some proper form though. V of t, right, is, it's the limit as h approaches 0 of s of what? Right? T plus h minus over h, right? All right, I'm racing you to it. We've done this a couple times. So I'm kind of cheating because I already did it, and now I'm just going to transfer it here. But you guys are going to do it on your own. I'll give you a little bit of a head start. Did you get a head start already? Okay. So very satisfying here, right? As everything like cancels out. Yes. So, well, I'll write slow here. Is my first step correct so far? Yes? And now, okay, this part I love. 16t squares go away. 1200s go away. Do you see the pattern now? Do you see how every single time it's the same exact thing? And then I'm going to cross out my h's. 1h from everywhere. So, all right, what's v of t then? Negative 32t. Any other answers? So v of t, right? v of t is negative 32t, but that's fine, but that's not what we want, because v of 4 is negative 128. Okay, fine.
Feet per second.
Feet per second, thank you. Well, because it was given in feet, I know. It's a, I have to sacrifice a little bit. I use feet sometimes. Now, so v of 4 is negative 128 feet per second. Who can tell me something about this? Yes.
At 4 seconds, the ball is traveling at a speed of, it's dropping at a speed of 120.
Okay, awesome. And why did you leave out the negative there?
Because dropping is 5%.
Right, so if it's falling down, right, if it's negative, then it's falling down. So the ball is falling down at a speed of 128 feet per second. Okay? At t equals 4, yes. Thank you for reminding me. At t equals 4 seconds. Okay? All right. Here. Okay, so we did talk about that yesterday. Yes. About, were you guys not here? Okay. Okay, so yesterday I reminded everybody about making wise snack choices. Namely, okay, audio related choices. Okay, when will the rock hit the ground? I don't know if we've done something like this before. When will the rock hit the ground? What does this mean, first of all? Okay, I heard some stuff here which I know have, I'm hearing all sorts of good things. Okay, so I heard set it to 0. Now, how do we feel about the word it?
We don't like it.
We don't like the word it.
Okay?
So set S of t equal to 0, right? So the rock will hit the ground when S of t is equal to 0. So 0 is negative 16t squared plus 1200. All right, I'll erase you to it. So t squared, how much? 8.66. So what does that mean? That's how many seconds it takes for the ball to hit the ground, right? So the ball hits the ground. Ooh. Oh, you're right. Let's keep it a ball.
Is that a rock in the question? Oh, yeah, the question is a rock.
Oh.
Yeah.
When did it, in my mind, did it switch to a...
It says how fast is the
Oh, I see. Okay, so, all right, let's make it a rock because we don't want it to bounce.
Oh, yeah.
Right. Yes, it does. Okay, so here, find an expression for the instantaneous velocity of the rock. Did I do this already?
Yeah.
Right, I did that already. So had I not read the questions before, I would have had to do this twice, one with 4 in there and one without. So go ahead and read the questions first, right? So v of t is equal to negative 32t. Okay, what is the velocity of the rock when it hits the ground? Right. Okay, so again, proper notation, V of 8.7 is negative 32. Okay, so does it make sense that the sign is negative here? Why? Right. Okay. All right. Okay, we're good here? Okay. Here, in this next one, we actually have a ball. An outfielder throws a ball toward home plate with an initial velocity of 80 feet per second. And I put this in here for two reasons. Namely, if I'm solving this, then... Okay. Oh, no. Why won't this go away? Oh. So if I can solve this, it means you don't need to know any baseball to solve this problem, right? And the height H, capital H of the baseball in feet, T seconds after the ball is thrown is modeled by this. And now it says find an expression V of T of the baseball. I purposely put in a variable of H here, right? Because when you're solving this problem, you're going to have little h, right? Because it's going to be h of t plus h. And I want you to be able to handle capital H and little h in the same problem without getting them confused. What I've noticed a lot of times is sometimes without thinking, without really paying attention, we switch between capital and lowercase, right? Yes, sometimes it could get you into trouble, okay? Right. T sometimes, right, and then, but if you have temperature, capital T, and time, little t, then we've got all sorts of t's, and it's important to be consistent with our variables, right? Okay, so, all right, V of t, it's on you. I'm going to stop the recording for a few minutes. V of 0.5, so that's half a second, right? It's, how much is it?
64%.
Is it?
Yeah.
Oh, yes. Okay, what does that tell you? Which way is it going? Well, this is height, right? So it's going upward, right? Okay, for what value of t will the baseball reach its maximum height? So here we go. We're talking about maximum height. What is the height function? Right? So when will that be a maximum? At its vertex. Okay, so let's graph that one. Let's graph that guy.
For this problem, this part we have to drop. And just let you know.
How else would you find it?
Like this part would be like a calculator.
It could be. Well, if how else would you do it? Right? Okay. Let's graph it and see what we can do here. So negative 16 x squared plus 80t, or x, plus 6.5. Okay. Possible window size. Let's do zoom 6, right? Standard, so we reset everything. Okay, that's useless, right? Because why? What's the independent variable here? Horizontal axis. What is it? Independent variable, horizontal axis is represented by, what is it? What does it represent? It's what? Can you do that later? Let's do that later. Have a seat. What is it? T. Okay, so what's a good time frame for t? Do we need negative t? No, so we can go from 0 to 10 seconds. That should be good enough, right? So think about a baseball, right? You throw it. I mean, it's not going to take years and years for it to get back on the ground, right? All right, so what about the y? What's a maximum height, do you think? Right, 0. And what's a maximum height, do you think? 100 feet? Well, let's see. So, listen. So, 100, we need to go a little bit more. Let's go to I'm going to leave a little bit more. I'm going to give myself a little bit more room here. Because then when I'm tracing and it's got the lettering up here, like the writing, then it goes over my vertex. Okay? All right. So how do we find the maximum here? All right. So let's do it. Okay, so where are your calculators? Okay, where is it? Okay, so 2.5 and 106.5. Great. What do those mean? Right? Right. Yeah. Okay, so, huh? If you say so. So, maximum height at t equals 2.5 seconds, right? What is the maximum height of the baseball? It's 106 what? 106.5 feet. Okay, now, we can obviously write this in a sentence. The maximum height of the baseball is blah, blah, blah. Or maximum height. Look at this. With this, we could give all the information. So h of, what was the time when this happens? 2.5 is equal to 106.5, right? So here we've got the x value, we've got the y value, we've got function notation, and all the possible information you could give. Okay? All right. This one's interesting. This I've never solved in pre-calc before. Okay? I'm going to give you a minute to read this. Okay? And then to read that first question. Just read the first question, right? A. And let's just think about that for a minute. So we have a square, and the length of it is changing. We don't care how, it's just changing, right? And every time something is changing, then we can find the rate of how it's changing, right? The rate of change. How fast is it changing?
Doesn't it have to be time?
Doesn't
that the rate have to be time?
It does, but take a look at what we're going to do here. So first of all, it talks about rate of change. So is this slope at a point? No? What? No, I'm sorry, it talks about average rate of change. That's what I wanted to highlight. Average rate of change. So is this slope at a point? No? What is it then? How are we going to find that? Did we? Right. So what was our equation for F average? Right? What was that generic? F of B, right? The generic one. F of B minus F of A over B minus A. And that was the slope. Do you guys remember? It was the slope of what line? Not the tangent. It was the slope of the secant line, right? And then eventually, you know, when our points got closer, slope of the secant line, slope of the tangent line were the same. You're going to hear this over and over and over again until sometime next year you are just saying it yourself, right? Okay, so this is just average rate of change. So, you know, we could say A average is the area at 5.6 minus the area at 5.4. Does order matter? Yeah. Okay. So I know you can do this. 31.36 minus 29.16. I want to get to the important parts here. So this is 2.2 over 0.2. And eventually, 11 is what we get numerically. Perfect. Let's talk about units. Okay? Tell me what units this should have. Inches?
Well, inches over like inches over length.
Well, it's area, so.
Units squared.
Inches squared. Inches squared over length.
But the rate of change is the inches squared.
Inches squared over length per unit of time. Per unit of time.
It's a rate. It's something inches squared.
It is a rate, so it should be per, huh?
Yeah.
You guys like, it's such a, like, it's so like, it's an instinct, it's something per something.
Oh wait,
So-
no. It's inch.
Okay, so I've heard the right answer. What are the units here? What is this? This is the area minus area, so it's what?
Inches squared over inch.
Inches squared. And the area here, this was just inches minus inches. Inches. So it's inches squared per inch, right? Does that just, okay, so here's a question, but I want you guys to answer. Does that just mean inch?
No.
So, like,
No.
why not?
Because you're talking about the area versus
Because it, okay, perfect. So it's rate, it's area versus something else. So now, a lot of times people would just be like, oh my gosh, this is so cute, inches squared, inches. Let's just cancel the inches and we get inches. No, because one is area, one is length, right? So when we talk about, when we talk about the area of something, so suppose each of these sides were 5. What would the area have been of that square? 25 square inches. You know that. What does that mean? That means if I had these tiny little tiles, 1 inch, 1 inch, how many of those would I need to fill that? 25 of them, right? So that's 25, and that's what squared inches means. And what is just inches? That's just a length, right? So the area of this would be, the units of that would be inches square per inch. In fact, I would also be prone to write this as 11 square inches per inch. Sure, mathematically is right. Just don't write inch.
Like if you tell us to like write it out, what would you say?
Oh, okay, so the average rate of change of the area is 11 square inches per inch. The average rate of change of your position is 11 miles per second. That doesn't seem odd to you because you've heard it so many times. But if you had heard this since you were a baby, then that wouldn't have sounded that foreign as well. It's just because, because you always think rate, it should be per time. Rate, it should be per time. But no, right? It could be anything per time.
If it's SQIN over IN, if you cancel out the INs and make it SQ.
No. I mean, you could, if you wanted to relinquish all the credit. Okay. Okay, so this one, we've done this millions of times. Instantaneous rate of change, right? What does that mean? Slope at a point. Fantastic. All right. I'm not even going to race you to it. You're just going to do it on your own. We're going to compare answers. So go. M here? 2x. So A of x is the area. I wouldn't. You want to right. And so what is the instantaneous rate of change of the area at the moment x is 5 inches?
Inches squared per inch.
Yes. Okay, now find it at the moment when, okay, so we're going to go above and beyond, when x is equal to, I don't know, 2 inches. What's m? For what? Right, so now, okay, let's think about this for a minute. The square is changing in size, right? The lengths are changing. The rate at which they're changing is 2x. It means, is it changing at a constant rate? Like, is the area changing at a constant rate? So for example, if you add 1 inch, right? Or if you add 2 inches, do you have the same change in area? Okay.
If it was x squared.
It just is instantaneous, so everyone.
Okay. When x is equal to 5, when x is equal to 5, right? Its rate is, it's increasing at a rate of 10. When x is equal to 2, it's increasing at a rate of 4. What does that mean? Let's draw some squares here. When they're 5, it's increasing at a rate of 10. Okay? When the sides are 2, it's increasing at a rate of 4. When is the area increasing faster? When x is bigger. When x is bigger. Look at you guys throwing around infinity. Right? So let's think about this. When x is bigger, the area is changing at a what? At a faster rate. When x is smaller, the area is changing at a right. Okay? So that's important. That's important for you to know that concept, right? That yes, this is changing, but it's not changing steadily. Sometimes it's changing faster, sometimes it's changing slower. Okay? So let me give you another example of when that happens. When you have a bathtub, right? And like the water is draining. The more water you have, the right? Versus like less water, like it won't leak out at the same rate, right? So just like here, okay, as the size, as the length of the square, as the length of the side is changing, right? Then it's increasing at a different rate. Okay? Yes? Okay. When else does that happen? How about your velocity? Right? Okay, so your velocity, let's say you're going at 5 miles an hour, and then you eventually increase to 50 miles an hour, okay? So think about you pressing on the gas pedal, right? So if you're applying like, a little bit of pressure, then, eventually your velocity is increasing. Now, is your velocity a rate? Your velocity is not a rate? It is. It's a rate of change of what?
Position.
Okay. So let's think about that again. Is velocity or speed a rate?
Yeah.
It's a rate of change of what? Your speed. I'm sorry. Velocity is a rate of change of what? Of your position, right? That's how fast you're changing your position. That's how fast you're going from city A to city B. Now, do you always travel at the same speed? No. You press on the gas pedal, you go faster, you go slower. Now, suppose you just floor the car and you go from 0 to 60 very, very quickly, or you go from 0 to 80 very, very quickly, or you go slowly, right? So now, listen to this. So now, imagine you're varying how fast that speedometer is changing, right? So you're increasing very quickly, or you're increasing very, very slowly. So what I'm getting at is I want you to think about this concept. That rate can change, but at different rates, right? Rate can change quickly or rate can change more slowly. Okay, so now what I want you to do is, do you remember the homework assignment from before, the handout? Take that out.